Alright, so the last section in this chapter deals with carbon-13 NMR. And again, I was able to, I had some technical difficulties with my printer. It's not out of ink, as you can tell clearly here, but for whatever reason it's deciding not to print some of these things. So it's faint, but I think you can see it, and I'll be reading it anyhow. So carbon-13 NMR. You get these signals for the exact same reason. The nuclei of the carbon-13 atom is spinning, and you apply an external magnetic field, the B0, and they can either spinning nuclei can either align with or against the magnetic field, and applying electromagnetic radiation in the radio frequency range flips those nuclei from either aligning with the magnetic field in the lower spin state to against the magnetic field in the higher spin state. So, well, carbon-13 is bigger than hydrogen, so naturally it takes larger energies, or parts per million, to do carbon-13 NMR. You notice the scale here goes from 0 to 200, whereas in proton NMR it was like 0 to, this would be about 15 maybe. You also notice that the background is a lot thicker. It's kind of noisy. If we look at, well, I'll show you a spectrum in just a moment. I didn't pay attention to the background earlier, but the background of proton NMR is much thinner and quieter. It's noisy here because of the oversampling, so you have to do this repeated times and then do this signal averaging, because only 1% of carbon, I don't know if you can read this here, 1% of carbon is carbon-13. Carbon-12 is silent to NMR. You have to have an odd number of protons in order for that to work, and that's why proton NMR works so well. A couple other differences now with carbon-13 NMR. Remember in proton NMR, here we go, nice quiet background, and the scale is only 0 to about 10 here, much smaller scale. You get all this splitting, right? And remember I said, well, if you have something simple like this, a methyl cyclohexane, the splitting pattern of the ring protons gets very complicated, and so you see this big mess here. Don't try to interpret that. But when you do carbon-13 NMR, that splitting disappears, and we're just looking at all the unique sets of carbons. So the methyl group's unique, the one on the ring that's attached to is unique. I guess if in the ortho position here is unique, meta and para. Again, you have a noisier background, but no splitting. No splitting, and also you notice the peaks are of all varying heights. The signal is related to the number of carbons, but you generally don't get integration data. So you see, for example, there's one carbon here, one carbon for number 1, one carbon here for number 2. They're different sizes, but still one carbon. 3 and 4 should be about the same size. 2, and yeah, they are larger, but 5 is also only one carbon, and it's pretty much, so you can't really make a whole lot out of the size of the signals in carbon-13 NMR. So essentially no integration. So just looking at these compounds, you're only going to get one signal. Both these two carbons are unique now, are identical. So remember, we're dealing with carbon-13. It's real easy to get mixed up and start looking at the number of hydrogens. These two carbons are unique as well. So you get two signals. Unique, unique, unique. This isn't, the first two examples aren't a whole lot different from what we would see with proton NMR, but here it is. If we were doing proton NMR, you'd say, oh, we get a signal from these hydrogens and these hydrogens, so just two signals. But in carbon-13 NMR, we're going to have 1, 2, 3 signals. For this one, these 3 carbons are identical. A, this guy is unique. B, and these 2 are unique, so C and D. So we get 4 signals for this one. You can't really make this compound out. It's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 carbons. I'll just put the carbons in. Carbons on each end are going to be the same. The carbons in these two positions are going to be, so let's call this A and A, B and B, and this carbon would be different C. So 3 signals. When we talked about geminal and cis and trans with the protons, you don't have to worry about that here, because first off, that was with protons, this is carbons, and we were talking there about splitting. There's no splitting with carbon 13 NMR, so we're just going to get 2 signals. There's symmetry down this guy, so 2 signals. A, B, B, A, and it wouldn't matter if they were cis or trans, simply 2 signals. So the signals arise for the same reason, the chemical shifts occur for the same reason. It's just that the chemical shifts are much larger. So remember, we were looking at hydrogens before, now we're looking at the carbons. They're all highlighted here, or maybe not highlighted very much, but let's see if I can use a pen here. So we're looking at these carbons, right? Alkyne, aromatic, carbonyl. Okay. And so for the same reasons, we see the benzyl, aromatic and carbonyl furthest downfield. Some more examples of carbon 13 NMR. Okay, so this is a 1-propanol. I can't remember if we did that one in the other lecture or not, but there's just 3 carbons. The one closest to the oxygen is going to be shifted furthest downfield, so C. So then there's this proximity effect, C, B, and A. But it doesn't give you any information with regard to integration, like 3 hydrogens versus 2 versus 2. No information with regard to their neighbors, so no splitting. It doesn't, I mean, the spectra are much simpler to look at, but in some cases harder to decipher because they really don't give you as much information. Okay. So with methyl acetate, again, there's 1, 2, 3 different carbons. The carbonyl carbon, Cb, is going to be shifted furthest downfield. This methyl group directly attached to an oxygen is going to be shifted downfield more so than this one. It's not directly attached to an oxygen, whereas this guy is. Okay, a little practice. Which carbon in each pair, if you can read that, absorbs further downfield? Okay, well, this one is directly, if we redraw this, ethyl ether, this one is directly attached to the oxygen, so this one is downfield. This will be upfield relative to this. Well, actually, you only get 2 signals. These 2 are the same as these 2. Here, well, this carbon is directly attached to a bromine. This carbon is directly attached to 2 bromines. So again, this one, it'll get an additive effect. This one will be downfield. Carbonyl, we saw earlier, way downfield. Relative to, now this is attached to an oxygen, but the carbonyl is much more electron withdrawing and it shifts it much further downfield. And alkene, just like with hydrogens, the alkene hydrogens are on a sp2 carbon are shifted downfield relative to a regular sp3 carbon, so downfield. And of course, you, if you're taking this course online, you have access to your book and your notes, and I don't know what I did with that table, but that table of chemical shift values for carbon 13 NMR is available to you. And here it says match, if you can read that, match each signal to its carbon in the given structures. Okay, so let's just label these. Are these alright, so it's 1, 2, alcohol group, 3, 4. So 4 signals, 4 unique carbons, right? 1, 2, 3, 4. Alright, so this is going to be tricky now. the carbon that's, let's just label these A, B, C, and D. The carbon that's directly attached to the oxygen in the alcohol, easy to pick out, right? This is the COH. The other three, not so much. Now, these two are closer to the oxygen than this one, so D has got to be the furthest upfield. But what about these two? There's no splitting pattern to help you, no integration to help you. But what you'll notice is this guy is a secondary, this one is a primary. Which one absorbs downfield more, the primary or the secondary? Well, they don't tell you that, and they don't give you that information here, but it would be the secondary absorbs further downfield. So this would be C, and this would be A. Okay, so chemical shifts, increased tertiary is greater than secondary, greater than primary. So downfield, upfield. Okay, here we have what, diethyl ketone, or it would be 3, 1, 2, 3, pentanone, 1, 2, 3, 4, yeah, 3 pentanone. Okay, again, okay, we'll label these A, B, C, D, and E. Well, A and E are going to be the same. B and D are going to be the same. C on the carbonyl, easy to pick out here. These two guys, again being primary and furthest away, is going to be upfield. So this is carbons A and E. They're equivalent. They give you one signal. Carbons B and D, again equivalent. They give you one signal. It says here proton NMR of E, proton NMR of F. I don't know what this is referring to. Okay, we're going back to proton NMR. The chemical formula here, C4H8O2, I think we did this one. So we have two isomers, each with the same chemical formula. It does say something about having IR absorbance. Okay, they each have an IR absorbance at 1700 nanometers. Sorry, not 1700 nanometers, 1700 wave numbers. Okay, so, alright, that tells us we have a carbonyl. So, let's try to figure out what these two isomers are. Again, C4H8O2, if it was saturated, it would be C4H10, so we only have 2 fewer hydrogens, so we know there's one double bond, that's the carbonyl. Okay, so there's a number of things it could be. It could be with 2 oxygen, it could be an ester. Like, ester like that. It could be an acid, it could be an alcohol, but you know what? They didn't mention in the IR spectra the broad peak that you would expect from the oxygen-hydrogen stretching. So this is not in the IR data. If they were to miss that, they would be really incompetent chemists. So let's assume there's no oxygen-hydrogen, so no alcohol and no acid. There's no mention of that broad IR peak from the oxygen-hydrogen stretching. We can assume it's not an alcohol or an acid. Some kind of ester. Okay, so 4 carbon. Well, let's just add these up. We have 23 plus 29 plus 30, 12, 5, 8, 82. So 8 units per hydrogen. So this is going to be equal to 2 hydrogens, 3 hydrogens, and 3 hydrogens. Okay. So 3 hydrogens suggests this. This is a singlet, so it's not next to anything else with a hydrogen. This is a triplet, so this has got to be next to a carbon that has 2 hydrogens. Well, there's these 2 hydrogens here. They're quite a ways downfield, and they're split into a 1, 2, 3, 4, a quartet. So these 2, right, are going to be next to a CH3, and they're going to be directly attached to an oxygen because they're so far downfield. So we get this. So these 2 hydrogens, this peak here, or this signal here, is these 3. The 29 here, this signal here, the singlet is from these. That's not a double bond. Okay, so ethyl acetate. For this one, all singlets, 30, 60, 80, 30, 60, 79. So 79 units, and again 8, so this is roughly, again, 10 units per hydrogen. So 2 hydrogens, 3 hydrogens, 3 hydrogens, all singlets. How are we going to do that? Okay, well, we know we have a carbonyl. Put a methyl group there, that's 3. That would be a singlet. But instead of actually being an ester, we can put CH2 here, and notice it's quite a ways downfield because it's next to that carbonyl, and it's attached to an oxygen. And then these guys, CH3, also downfield quite a ways, attached to this oxygen. So this is how we get the 3 singlets. So it's not an ester, it's a polyfunctional molecule. It's got a ketone and an ether.